Hi everybody, welcome to this is actually 6. It used to be Unit 7, but we changed things around for our COVID unit. So depending on when you're watching this, it might be Unit 6, it might be Unit 7, who cares? It's all about equilibrium. Now, this is a brand new topic probably for most of you. If you were taking the 332 class, you probably had barely, if any, exposure to this topic at all. If you were in the 338 class as a sophomore, then you probably only had very, very, very limited exposure to this. So there's going to be a steep learning curve at the beginning here while we develop a language in order to discuss the important phenomenon that will be equilibrium. In fact, equilibrium is probably the number one topic on the AP test. Everything that we're going to do from now till the end of the school year is going to have to do with variations on the same theme of equilibrium. There are going to be about 5 or 6 different flavors of equilibrium that we are going to learn about here. So today what we're going to do is we're going to see if we can't understand a little bit of the basics that is involved with these guys. So buckle in. This one's going to take a while. And you might want to follow along a little bit with this lecture notes so that you can make some marks just like I do here. All right, so if you remember back from our last unit in kinetics, we were used to seeing graphs like this, right? And what we did was we spent a whole unit talking about these parts of the graphs here where they were changing, right? But it turns out that there is another interesting part of the graph, and the other interesting part of the graph is where the action seems to stop. And if you take a look at it, it really does seem to imply that the action has stopped after that dotted line, because everything that occurs after that dotted line is a straight line, which means that the concentrations are no longer changing. So it appears at that point, at any rate, that the reaction has stopped. And that is certainly a possibility. If the reaction only goes so far and then doesn't go any farther, then you could certainly infer from that data that the reaction is simply not proceeding anymore. And if it's not proceeding, then the concentrations of everything doesn't change, and we can explain it that way. But it turns out that there's another explanation for that. Now, to explain this explanation, or to justify it, do you remember the game Red Rover? Red Rover, Red Rover, send Johnny right over, right? I don't know if you guys ever played Red Rover. But basically what you would do is you would set up in a couple of lines and you would all lock hands. And then one side over here would say, hey, Red Rover, send so-and-so right over. And then one of the people over here would have to try to run over to the other side. And all these people over here were locking hands together. And this person would have to try to break through the hands there, which caused no small amount of injuries, and it was one of the most torturous games that they ever made us play in elementary school. I mean, that and dodgeball was basically the Lord of the Flies. But basically what you would do is you would have a person go from one side over to the other side and try to break through. And then, of course, the second side we get to call back. So you would say, Red Rover, send a person right over. So all over the person goes, and now he's over there on the right-hand side, right? But the round isn't over until side B has to send a runner back. And so you would say, Red Rover, send so-and-so right over, and then that person would run over and try to break through the lines. And if we examine where we started versus where we ended here on this, once you send a person over one side or the other side, we have the same number of people that we started with here that we ended with here. So maybe, just maybe, instead of no game being taken place here, right, maybe what's actually happening is that there is a forward reaction occurring and there is a reverse reaction occurring, and they are occurring at the same time and they are occurring at the same rate. So that every time a side A turns into a side B turns back into a side A. So the ultimate net effect of it is not that there's no reaction taking place, it's that the sides remain the same because for every one of these guys that goes this way, one of these guys goes this way, and there's no net effect in it. This is called a dynamic system. And a dynamic system means that it's not that the reaction has stopped, it's that the rate of the forward reaction and the rate of the reverse reaction are the same. That's really what it means to be at equilibrium. Think of yourself in a rowboat, and that rowboat has a leak in it, I should say. And you're in that rowboat and it's starting to fill up with water, and you get a pail. And you are able to scoop the water out of the rowboat as fast as it comes in. Well, there's a whole lot of work occurring there. It's just that it's not getting very far because you are paling out the water as fast as the water comes into the boat. There is no net change of what's going on here. So, what we are going to say is we are going to say that in order to be at equilibrium, there are a couple of different requirements, and our list is going to grow over time here. And those requirements are that the reactions have to be reversible. Obviously, if a reaction just goes one way and it cannot go backwards, then it can't be in equilibrium. So it's got to be reversible, and it's going to be dynamic. And again, that dynamic means that the rate of the forward reaction and the rate of the reverse reaction are actually the same. And it doesn't really matter even how fast that goes. And I want you to really pay attention to this because equilibrium does not mean equal amounts. Please note here that side A and side B do not have equal amounts. So equilibrium does not mean equal amounts. That's the most common mistake that people make, is they'll say that equilibrium is here because that is where the amounts are equal. Equilibrium does not mean equal amounts. Equilibrium means that the amounts don't change, because at these points, the rate of the forward reaction and the rate of the reverse reaction are the same. That's what they mean. All right? And it can be very fast, too. It can be a fast equilibrium. You can have 1, 2, 3, 4 people all red rovering over to side B. And at the same time, you have 4 people, 1, 2, 3, 4, all red rovering back over to side A. That's a very fast reaction, but the ultimate effect of it is nothing, because when it's all said and done, the green guys are on the left, the pink guys are over on the right, and ultimately nothing has changed. So to be at equilibrium means that you have a reversible reaction, and then the forward and reverse reaction rates are equal. The rates are equal. That's where the term equilibrium comes from. It means that the rates are equal, not the amounts, the rates. To be at equilibrium, you don't have to have the same amount on both sides. You have to have the same rate as the forward reaction and the reverse reaction. All right, well, how are we going to predict this? Well, let's do a little bit of an experiment. I really wish that you were able to be in class for this one, because this is one where actually tactily, manipulating everything, you get a lot of real-world experience from this. But let's take a look at what we've got here. We've got 2 different straws. We've got a big blue straw and we've got a small white straw there. So please note that the big blue straw has a much larger capacity to move water than the small white straw does, right? Now, does that mean that if we were to put the straws into the graduated cylinders here and start moving water, putting our fingers over the top of it, capture an amount of water and start flipping them, does that mean that all the water would be able to move from the left side over to the right side because the blue is bigger, right? Well, not necessarily, because again, think about it. What's going to happen is that the blue straw is going to start moving things over from left to right. But then the white straw is going to start moving things back over from right to left. And as you start to use up the liquid in the blue cylinder, there's going to be less and less and less liquid available for it. And as you start putting the liquid into the white cylinder, the products one over here, there's going to be more and more and more liquid for it to choose from. And so what's going to happen is that after some time, you're going to reach a point of equilibrium. That even though the blue cylinder here can theoretically take more, there is less of it. And because there is less of it, the rate on that has gone down. And the white one here, there is more of it. And because there is more of it, the rate is going to go up for that one. So if the blue rate goes down, so the blue rate started up here and it starts going down and down and down and down and down. And then the white rate started down here and it starts going up and up and up and up and up. Eventually, you will reach a point where the blue rate and the white rate equal each other. And if the blue rate and the white rate equal each other, then the amount that is going from left to right and the amount that is going from right to left are going to be the same, and we will have reached equilibrium. Check it out. So here is our blue one, and it's going down and down, 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 down. Now we reach that point, while the white one, again, I can't put it in white on this, but I'll put it in red. They get up to here. Now that's where they are the same amounts, but the same amounts does not mean the same rates. So the white one continues to go faster and faster, and the blue one continues to go slower and slower, and eventually you reach a point where they have stopped changing. So check it out. At this point, they have basically stopped changing, and the data backs it up. This is the blue that's here, and this is the white one that is here, all right? And so the blue one gets less and less and less and less and less and less, and then it hits 10 and it doesn't change anymore. And the white one gets higher and higher and higher until it hits 15, and then it doesn't change anymore. So equilibrium does not mean that they are equal. Equilibrium means that however much water is being transferred from left to right is the same as the water that is being transferred from right to left. And so what is happening at this point here is that the rates are equal to each other. And that is when we have reached equilibrium. Because equilibrium does not mean equal amounts. Equilibrium means equal rates. All right. Now, that's one experiment. But if there's anything to this, we should be able to repeat the experiment with, any number of different amounts of liquid. So let's repeat the experiment. But this time, instead of starting, you'll notice here, with all of everything over on the left-hand side, we're going to repeat the experiment. And this time, we're going to start with everything over on the right-hand side. Everything's over here. So we're now going to do the experiment. We're going to take some liquid and move it from left to right, and take some liquid and move it from right to left. So what's going to happen is that the blue is going to get more and more and more and more and more up until it gets to a point, and then the white is going to get less and less and less and less and less up until it gets to a point. And check it out. Oh, wait. The white one got down to 15, and the blue one got up to 10. Like so, right? So if we check out the amounts that are there, it was 15 and 10. Now, why does that sound familiar? Because 15 and 10 was the same amounts that we ended with up here in our experiment. The blue one got down to 10, and the white one got up here to 15. And it was at that point, 15 and 10, where equilibrium was established. So check out that graph. And check out the other graph and compare them, you'll notice that they both ended at the same spot. The white one ended at 15, the blue one ended at 10. So it turns out that the 10 to 15 ratio, or more likely the 15 to 10 ratio, was the correct ratio of the amount of water in each cylinder for this particular experiment. So it turns out that the third aspect of equilibrium is that there is a stable ratio of products to reactants that will always be reached. There will be some amount of products and there will be some amount of reactants, and as soon as you reach those amounts, and there is a relative ratio of the products to the reactants, the P over the R that are here. As soon as you reach that amount, that is where equilibrium will occur. So there are three aspects of equilibrium that are important. The first aspect is that the reactions have to be reversible. If for one or another reason that the reactions can only go one way, then it will not be at equilibrium. Number two, they are dynamic, which again means that they have not stopped. It just means that the forward and the reverse rates are equal. And then our third aspect of equilibrium means that there will be some amount, there will be some stable ratio of products to reactants that will be the perfect amount. And when that perfect amount is reached, a certain amount of products and a certain amount of reactants, and when that certain amount has been reached, that's when the rates are going to be the same. So what we're now going to do is we're going to look at a little bit of the math of this, and we're going to develop the KEQ. So let's look at three different experiments that are here. In our first experiment, when we have hydrogen and iodine going to hydrogen iodide, we're going to take 2 and 2 and 0 for the hydrogen and the iodine, and then we're going to start with none of the hydrogen iodide down here. So again, that's 0 down here. And we're going to start with 2 for these guys. And then we're going to run the experiment, and the reactants are going to go down and the products are going to go up, and we're going to reach a certain amount, right? And those certain amounts, I guess, are 42, 42, and the 3.16 to get to here and here. That doesn't tell us much off the top here, right? That doesn't look like anything normal is occurring here. Nothing about those numbers jumps into my brain and goes, oh, well, that makes sense. Well, let's do another experiment then. Now, in experiment number 2, we're going to start with all of the reactants instead. So we're going to start with all the products instead. We're going to start with 2 of the products, and we're going to start with none of the reactants here. And then we're going to run the experiment, and we're going to get their numbers. And by the time they reach equilibrium, they've reached apparently 158, which is this guy, and then 0.212s, which are these guys here. Again, I don't know that really tells me much in comparison to the first one here without some larger context. And just for completeness' sake, let's go ahead and make things a little goofy. We're going to start with 2 and 4 here. So we're going to start with 2 and 4 and none of these guys. And then we're going to run the experiment, and apparently we're going to end up at 0.12 here. And we're going to end up at 2.12, which is the iodine here, and we're going to end up with 376, which is this guy here. Now again, these are 3 experiments that ended up with 3 very different sets of numbers, and you look at them and you say to yourself, there's not really any correlation between them. But it turns out that there is. It turns out that in all of these sets of numbers, there is a correlation between those numbers, and those numbers, if you know the correct deciphering key. Now, what is that correct deciphering key? Remember, equilibria are going to be established when there is a stable ratio of products to reactants. There's going to be some number that occurs, some mathematical ratio, some mathematical value that makes it so that everything works out. And in looking at this, it doesn't appear off the top of your head that there's any real mathematical obvious relationship between them. But it turns out that there is. And it turns out that that ratio is going to be the HI squared divided by the H2 and the I2. Right? So it's the HI squared, and then it's the H2 and the I2. And you might say to yourself, okay, how was I supposed to figure that out? Well, let's look at the balanced equation. The HI is over here on the product side, and there's a big 2 in front of it. So we're going to go ahead and take that products of the HI, and we're going to square it because there is a 2 in front of it. And then we're going to see that the H2 and the I2 are on the reactant side, so we're going to divide those guys down here. And there's an invisible 1 and 1 in front of them, so we're going to raise them to the 1 power and the 1 power there. Now, it doesn't seem like it's going to work, but if we were to take all of these numbers, all of these numbers, and all of these numbers, and plug them into this equation that's here, it turns out, here are the results of that. We get about 56, 56, and 56, depending on where you round and so forth and so on. In all three of those experiments, you get about the same number. Oh, that is a constant number. And if there is a constant value from very disparate sets of data, you know that you are on to something. So, if we cut to the chase, what we are going to do is this. You're going to take any equilibrium equation. And for any equilibrium equation, you're going to have some things on the reactant side and you're going to have some things on the product side over here. If you want to figure out what the correct ratio is, if you want to figure out what the correct math is for this system, what you do is you take each of the reactants that is over here, and then you raise it to the exponent that is the stoichiometric coefficient in front of it. And then you multiply it by the other thing that it's with. So then we're going to have d raised to the power of d there. And then we're going to divide everything by the reactants. So A is a reactant, so it's going to go on the bottom, and it's going to be raised to its power A. And then you're going to multiply on the bottom down here the B aspect of things, so that, and then raise it to its power like so. So all you're going to do is take products over reactants raised to their powers. So that's why when we did up here, if I want to know what the K is, the K is going to be the hydrogen iodide, and we're going to square it because it's the products, and there's a 2 in front, and then we're going to divide it by the H2 multiplied by the I2, because those are the guys on the reactants, and there's an invisible 1 in front of each of those guys, so we're going to raise it to the first power. So it's going to be products over reactants raised to their powers. Now, there's a couple of things that come from this, the first of which being 2 new terms, and those terms are product-favored and reactant-favored. In a product-favored reaction that's here, we have a lot of products, you'll see, and we have very few reactants. And if we have a lot of products and we have very few reactants, knowing that the products are going to be big and the reactants are going to be small, then if you have a big number divided by a small number, then you're going to end up with a big number that's bigger than 1. And so a product-favored reaction is one that the K value is larger than 1. And so product-favored reactions tend to go to the right-hand side toward the products and away from the reactants. If it is a reactant-favored reaction, then what do you have? You have a small amount of product and you have a big amount of reactants, and small divided by big is going to be a small number that is going to be less than 1. And so there's going to be lots of reactants and few products, and it's going to be favoring the substances on the left side of the equation, the reactants, because there are lots of reactants and there are very few products. So if you have a product-favored reaction, then your K is going to be lots of products with very few reactants. It's going to be a big number. If you have a reactant-favored reaction, then you have a small amount of products, a big amount of reactants, and so it's going to be a small number. It's going to be less than 1, where product-favored is going to be larger than 1. Now, remember all those flavors of K that I told you about? We're going to get into 2 different types of those flavors right now. The large umbrella term is KEQ, and it's going to turn out that there are 2 different flavors of KEQ, KC and KP. KC is simply based upon the concentrations of things, and KP is based upon the pressure of things. So if you're going to do KC for substances, then what you're going to do is you're going to put everything in brackets, because remember that the brackets stand for molarity or concentration. So if we examine this, we've got the reactants over here and we've got the products over here. So if I want to know what Kc is, then all I have to do is take each of these substances that are over here on the product side, and put them in brackets and raise them to the power that is in front of it, which would be a 1 in this case. So you'll notice that in this case, I've got HSO3, which is here, and it is raised to the first power because there's a 1 in front of it. And then I'm going to multiply that by CO3 negative 2, because again, it's still on the product side. And I'm going to raise that to the first power. There's an invisible 1 there because there's an invisible 1 in front. And then I'm going to divide it by the reactants, which are over here. So I've got an HCO3 that's going to be down here with, again, an invisible 1, and so there's an invisible 1 exponent up here. And then the SO3 negative 2 is also on the reactant side, so that's going to be on the bottom. And because there's an invisible 1 in front, there's going to be an invisible 1 that is there. All right, so that would be Kc. Kp is the same thing, except it's based upon the pressures rather than the concentrations. So instead of putting it as the brackets like we did up here for the concentrations, we're going to use pressure iconography instead. So this only works for gases, so pressures are only for gases. So I got a gas, and a gas, no problem. And if that's the case, then what I have here is I have nitrogen, which is a product. And so I've got the pressure of nitrogen, and there's an invisible 1 here, so it's raised to the first power. And then I've got hydrogen here, and hydrogen's a product, so it's going to go on top. And so it's going to be the pressure of hydrogen, but there's a 3 in front of it, so that's going to be raised to the third power. And then because this guy is a reactant, he's going to be down here at the bottom. And because there's a 2 in front of it, it's going to be raised to the second power there. Now, you might see it written this way instead, because sometimes drawing these things out on the computer is a pain. So you might see it written this way instead, where instead of putting it in normal equation form, they might put it this way. Kp is going to be equal to the pressure of the nitrogen times the pressure of the hydrogen cubed. And then instead of dividing by it, they might multiply it by the pressure of the ammonia to the negative 2, remembering, of course, that negative means that it's in the denominator down here as a positive. So that goes back to your math information that you knew from your calculus classes and so forth. So if you have a negative 2, it means that it's really 2 in the denominator, right? Or, again, they could take this and they could put it up here, and they could, there we go, they could put it as a negative 2 instead in the numerator. So if it's in the numerator as negative 2, it's the same thing as being a 2 in the denominator down below. All right, one last little trick for this. Solids and liquids don't actually have a concentration. And you might say to yourself, but Smith, we use water in concentration all the time. Yeah, that's the solvent. So what's the concentration of pure water? It doesn't have one. Water is used to add or subtract the amount of solvent that is there, and that will change the concentration of the solution. But solids don't have a concentration and liquids don't have a concentration, and so consequently, you will omit them from the equation. Don't even count them. Pretend they're not even there. So if we take a look at this, and I wanted to know what Kc was, then I'm going to do products. So there's my lead ion, no problem, and there's an invisible 1 in front, so I'm going to put a 1 there. And then multiply by the chlorine, and there's a 2 in front, so I've got to make sure that I put it as squared. And then I'm going to divide that by the reactants, but the reactant is a solid. And because the reactant is a solid, we just pretend it's not even there for the purposes of our equation, and so we're done. This is the equation that we have here for Kc for this reaction. It's products over reactants, and you omit solids, liquids, and solvents. You pretend they're not even there. So this guy here, if we were to do that, and if I wanted Kp for this guy, then I would do products, but notice that the only product I have is a solid, so I omit him. I pretend he's not even there. So the only thing I'm going to put on the numerator is a 1, because if I put a 0, obviously I can't do any math with it, so I'm going to put a 1. And then over here, I've got another solid, which I'm going to omit, like so, and make him go away. And then this guy here is a reactant, and there's an invisible 1 in the front, so I'm putting him in the bottom, in the denominator down there. Or if I wanted to, I could say that Kp is equal to the pressure of carbon dioxide to the -1. And then again, that -1 that's here would indicate that that pressure is going to be in the denominator down below. So, our summary. Our summary is that for any reaction, A and B goes to C and D, you do products over reactants raised to their powers, like so. You ignore solids and liquids, and you can either put it as concentration or as pressure. And if you've got a big number, it's product favored, and if you've got a small number, it is reactant favored. I know that was a long discussion, but those are the basics and the introduction to figuring out how equilibrium works. And then what we're going to do now is we're going to take these basic ideas that are here, and we're going to solve